for some places.
Gotcha. And then another question, since I wasn't able to make the earlier part, are these slides available elsewhere, or?
I'm pretty sure they'll be.
Yeah, they'll be online still at the top as a video.
Okay.
Yeah, thanks. Yeah, so you'll be able to see that whole intro part. You didn't miss a thing. Well, yes.
You mentioned the idea of marketing yourself as a data scientist on LinkedIn. What do you think are the skills, the bare necessities to market yourself like that?
Bare necessities.
Yeah.
Oh,
I'm
so-
sorry, like what? Because you mentioned that as long as you have the skills to back it up.
I mean, I think that's going to vary by job, right?
Yeah.
But I mean, I can tell you, usually what I'm looking for is Python and R for sure, like being able to program in those languages. I usually look for machine learning, right? Because I'm in a hardcore machine learning group. And I usually start looking for like specific libraries too. Because if you can talk shop with me about pandas and matplotlib and seaborn and all that stuff, that means you've probably jumped into the field a little bit and you've worked with those a bit. In other jobs, they're going to look for, like BigQuery or Hadoop or all these other, fancy database technologies, which I frankly don't care about. I've never needed to use. But some places, they live on that, So I think it's, again, when we break it down by the different kinds of jobs, the skills you look for are going to vary pretty tremendously. But for sure, Python and R. Like if you've learned both, that's a really great sign. It means you're not going to come in as, what's the term I'm looking for? As a zealot for either language. That's a great way to start a war within a lab or within a group, is to say, my language is better. Yeah, so we definitely try to avoid that. Yeah, any other questions before I hop on? Awesome. Okay, well, we'll have time for questions afterwards as well. Yep, so let's go ahead and jump into the next section. This is basically my research over the past year and a half or so, and actually we're continuing this project as well, expanding it onto a large computing cluster and everything. Boy, this isn't my research. This is just a funny plot. So this was I found this plot on a local company's website called RJ Metrics, local to Philadelphia. That is. I don't know why I pointed here. I keep thinking I'm in Philadelphia. But anyway, they did a funny analysis of LinkedIn, and they looked at the number of self-reported data scientists on LinkedIn over time. And what they saw was that in the past 5 years, the number of data scientists listed on LinkedIn has more than doubled. Right. So we have a lot of people getting into data science. I mean, we have data science graduate programs and everything coming in now. It's been really amazing watching the field grow. What this means is, as data science and machine learning comes to the forefront of academia, business, government, everyone wants to use it nowadays, we're going to need to make the tools, data science tools and machine learning tools, more accessible to people, right? When you first get into the field, it's pretty brutal, like to learn scikit-learn. What's going on here? The examples are terrible. I can't figure this out. So that's one thing I wanted to focus on for my postdoc, right? I wanted to focus on how can we make these tools more accessible to people, and I'll show you exactly what I'm talking about here. And so yeah, basically, when I started my postdoc about a year and a half ago, a couple weeks in, we were trying to figure out a project to work on, and I pitched this crazy project. So that's what I'm talking about here. And I was reading around, just trying to figure out what's a good, what's a good thing, general problem to work on for the field of data science, for the field of machine learning. And I was reading all these books. this is a quote from one of these older books that says, machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Have you ever read anything like that in a machine learning book before? If you've read a machine learning book or read it online. We love to sell machine learning as like this magic, right? This magical tool that's going to solve all our problems, especially deep learning nowadays. We love to overhype deep learning. But now that I've been in the field for a while, I know that anyone who says something like that, and I've literally said things like that, is full of crap, right? They're overselling. And that's because if we look at a typical machine learning pipeline specifically, we know that it's much more complex than just applying machine learning and you're done, right? So this is a little depiction of a standard machine learning pipeline. Typically, we start with some raw data there on the left. You know, we get a data set from our advisor, from our boss, from a client, or whatever else. And typically, it's going to be in some really disgusting format because they have no idea how to organize data. They just collected it. And so we're going to spend a lot of time, some people say 90% of our time in this data cleaning step, right? Where we're just trying to get the data into a nice, like tabular format that we can maybe open up in Excel, or you shouldn't open it up in Excel, but in that format. Then once we get the data into that nice little format, we're going to apply all kinds of transformations to that data. Right? We're going to maybe apply feature selection to remove redundant or useless features. We're going to do some feature processing, maybe scaling them or something like that to make it more amenable for machine learning algorithms down the pipeline. Or we'll even do some feature construction, combine features in a useful way or something else that'll allow the machine learning models to better capture the signal within that data, right? So we're going to apply all kinds of these pre-processing operations. Then, of course, we have to go to this model selection step, right? So if you looked in scikit-learn or the corresponding R libraries, you've probably seen that there's tons of machine learning models out there. And you've probably also wondered, like, oh my God, when do I use these? Which ones do I use? When's the right one to use? That's that step, right? You have to figure out what's the best model to use. And then also, once you've selected that model, most machine learning models come with parameters, right? So if you're familiar with like a random forest, it's going to have, let's say, the number of trees in the random forest, the number of decision trees, maybe the depth that you allow them to grow through, all kind of, and that's a pretty basic machine learning algorithm in a sense. Not much to tune there, but even that algorithm has parameters. So, you're going through this data cleaning step, pre-processing features, choosing a model, then optimizing all the parameters of those preprocessors and that model, and then you have to do some sort of validation step at the end there, right? Where you actually validate your final model on data that's never seen before, right? It's important to know this concept of, cross-validation or training and testing data set, right? You do all this initial fitting of your model on the training set, and then you validate it on a data set you've never seen before, and that's when you realize, wow, I did this completely wrong, I massively overfit my data, and you go all the way back to the beginning again. If you're lucky, maybe you can go back to the, to the end of the data cleaning step, and just start again at the feature preprocessing and the model selection and all that good stuff. So my point here is that machine learning can be tedious, and machine learning can actually take a lot of manual programming, despite what we, despite how we try to sell it. And so I really want to drive this point home with a few more examples. So who's familiar with this MNIST data set? I'm sure you've worked with it. It's basic image classification, nice toy problem. Right, so this is basically a data set that they collected, I believe in the mid-90s, of handwritten digits, 0 through 9. And they scaled them nicely and squashed them down into, or pressed them down into a 28 by 28 image in a fairly standard format, except that you can see that some people have some really crazy handwriting, right? And the goal here is that if you feed all the pixels of each individual image into a model, can it tell you what digit that is, right? So the upper left one there, you give it, the 28 times 28 pixels into the model, can it tell you that it's a 2? Who's familiar with random forests? Okay. So I guess I'll just say, basically, random forests are a fairly basic supervised machine learning model, right? They can take features and try to learn some sort of mapping between those data features to, predict some sort of class for those features. So this little game that I want to play here for this MNIST digit recognition problem is, can a random forest classify? So by a show of hands, do you think a random forest can achieve a reasonable accuracy on the MNIST data set? And not much confidence in the random forest. And so yeah, I was kind of hinting at it when I talked about this problem. This is a pretty simple machine learning problem, right? If you feed it the 60,000 training images that come with the data set, and then you test it on the 10,000 testing images that never saw before in the training step, if you use a random forest with the default scikit-learn parameters, which is just 10 trees, which to me is crazy, you'll still get 94% accuracy right out of the box, which is, that's pretty good. However, if, let's say you do a little bit of model tuning, right? You tune your parameters, and if you've tuned a random forest before, it's a bit of a joke to tune the number of trees. It's just sort of obvious that you give it as many trees as you have memory or as you have time. But let's say you give it, order of magnitude more decision trees to work with. You get 1,000. You can up your accuracy to 97% doing some really basic model tuning, right? And if you're thinking, 3% accuracy, whatever, that's not that big of a deal. Well, think about the potential application of this, right? This is being very commonly used now by the U.S. Postal Service to recognize our really poor handwritten digits whenever we're sending mail, right? So if you think about, let's say, 1 million characters come through, one post office branch a day, and it misclassifies 3% of them, that's 30,000 misclassified numbers in just one day in just one office, right? So if you think about the scale that machine learning algorithms can work on, 3% accuracy can be pretty tremendous. So my point from this little example here is that parameter tuning of your machine learning model can be a pretty important task. Okay, the next data problem that we're going to play the kind of random forest classify game with is time series analysis, right? So each of these lines, we break that down into a set of features, right? So each of these lines has the same number of points. We basically feed those points into the machine learning algorithm, and it has to tell us, is there a hill or is there a valley in this data set, right? So up here on the top, we have a hill, and right over here, you see it? Yeah, okay, good. We have a little valley, right? So it has to be able to analyze this very simple simulated time series and tell us if there's a hill or valley. So, if we do the normal train testing, cross-validation, all that good stuff, can a random forest achieve reasonable accuracy on this data set? Let's show of hands. What do you think? I gave you guys false confidence in the random forest. No. So, random forests, they weren't necessarily designed for time series analysis. So if you use a random forest with 1,000 decision trees, you get about roughly 62% accuracy on this data set. However, let's say you go, well, let's try a different model. Like I hear a logistic regression can maybe work well on this kind of data. Without any tuning or anything, you just use default parameters, you can get almost 100% accuracy just by using a different model, right? So when you first learn about random forests, you might think, wow, they're amazing. They solve all the problems. That's partly true. They solve like 2/3 of all the problems or 80% of the problems pretty well. But there are many problems where other models work well. So another point here, important one to remember, is that model selection is also a really important step in designing machine learning pipelines. So, yes, like I usually default to random forest when I'm analyzing data. They're a nice, simple model, great place to start. But always think about, oh, I should actually try other models as well. That's why there's like, hundreds of different machine learning models out there, because they're all for these little niche problems that we've run into over the years. Okay, the third problem that we work on is just a slightly harder version of that time series classification data set, where now we've added noise, right? So we still have, the top here, we have a little hill here, a little valley over here, but it's much more noisy, right? So it's a harder problem, harder version of the previous one. So let's show of hands, can a random forest classify it well, achieve reasonable accuracy? Good, everyone's paying attention. Or not paying attention, just not raising their hand, either way, but I'll assume the best. Yeah, of course, because it's a noisier version of the previous problem, it gets about 58% accuracy, right? Which is just barely above flipping a coin, right? Because this is, the same number of hill and valley records in the data set. However, let's say prior to passing it to a random forest, you decompose each of these time series with PCA. Right? If you don't know what PCA is, don't worry about it. It's a feature processing step. Google it later. It's a very useful technique. But by doing that, you can get 94% accuracy, right? So the important point to take away here is that feature preprocessing is also a very important step of machine learning pipeline design. So let's recap what we just went over. Whenever we're approaching a machine learning problem, in addition to worrying about all the data cleaning and all that fun stuff beforehand, we should always tune the parameters, or sometimes we call them hyperparameters of our models. We should always try out many different models, not just our favorite ones. We should also explore numerous feature representations of our data, so we can pre-process with PCA, or there's, just look in the scikit-learn repository or the scikit-learn documentation. There's tons of ways to pre-process your data. However, I guess that's part of what I just said here. There's thousands of possible hyperparameters for each model. There's dozens of machine learning models and dozens of popular pre-processing methods, which, if you wanted to try all these out, it's basically impossible. Right? You would spend till the end of eternity trying out every single combination out there. So, ultimately, my point of that section is to say, machine learning can be tedious, right? It's very powerful, very useful technique, but there's a lot of, human intervention, a lot of programming that goes into it, despite how we love to sell it. So, cool video game video. So at the same time, I looked at these challenges in machine learning, especially challenges for newcomers to the field, and I said, wow, I'd really like to fix that problem. And I also saw also during that time, I've been an evolutionary computation researcher. Neuroevolution, if you've seen this video before. And so we've seen some really cool advancements in this field, right? So this is called MAR.io, and basically, Google it if you haven't seen it before. It's a pretty cool video. Basically, they use this optimization method called evolutionary computation, and all by itself, it was able to learn how to play Mario just the same way we do, right? It looks at the pixel inputs, and then it decides whether to jump, when to move, and all that good stuff. And it learns to play this game really, really well. There we go. This is actually my own personal silly application of evolutionary computation. I used it to basically solve the Where's Waldo problem. Which the Where's Waldo problem is, man, we spend way too long trying to find Waldo in those old Where's Waldo books. Does everyone know what Where's Waldo is? Are people? Yeah, cool, okay, so it's still a thing. That's good. I'm not that old yet. Yes. So here, basically what we did is we went through a bunch of the old Where's Waldo books, and each of those little points on there represents where Waldo was on one of those pages. And then we treated it as as we call a traveling salesman problem, basically trying to find what's the shortest path we can look along the page, find Waldo as quickly as possible. And so I use this evolutionary optimization method to solve this, pretty quickly. This is showing the simulation of it solving it. And basically we found there's some nice path you can follow where you can typically find them within about 10 seconds, right? So if you have kids and you want to really impress them, this is, I think, a great way to do it. Don't tell them about this and be like, look at how fast I can find Waldo. And they're like, wow, you're amazing. You're so cool. And it'll all be thanks to this post right here. So you're welcome, future parent you. Or maybe present parent you, either way. Another really neat application of evolutionary computation that we've seen, which this is actually the coolest one to me, despite it being a silly little antenna. That's what it is, it's an antenna. So there was a challenge within NASA to design antennas for some of their satellites that they were sending up. And they had some engineers that had years and years of experience designing these antennas, and they came up with, smart but pretty basic designs. And then one guy who was an evolutionary computation researcher there said, hey, why don't we just, we know this evolutionary computation method works pretty well for optimizing things. This was even before the video game days, the Mario days. And it came up with this crazy, crazy looking design, right? I don't think this is anything a human would ever design. But then when they tested it in the simulator, and when they tested it in the real world, it worked way better than anything the engineers had ever designed before. So, they basically threw out all the engineers' ideas. The engineers were completely wowed. They're like, oh man, I see the genius of this. And the guy was like, yeah, I just ran an algorithm and that did it for me. But so this thing is actually flying up in space now on some of the NASA satellites, right? That's pretty cool. That's a pretty cool application. But it's, of course, a tiny little antenna, but it's a small win. Another cool application of evolutionary computation that I've seen, specifically called genetic programming, is basically making it so a computer can do the programming for you. You know, if you're in like beginner programming classes, you must be thinking, wow, this is so great. You know, I just tell it, solve this problem for me, and it writes the code for you. And so, unfortunately, I couldn't find a good like video of that. So this is actually just someone coding on YouTube, and I fast forwarded it. But there are I'm a part of the genetic programming community now. I've been telling people like, oh, we got to make a cool video. But that's like a typical thing in academia. We say, oh, we got to do this, and they say, yeah, you should do it. You should, and then no one does it. But anyway, so this is a video we have. We do have programs out there that automatically write software for us. They can also, you know, fix software bugs and things like that automatically at a fraction of the cost of what it would take for a human to do the same thing. So I saw these really great advancements in my field, right? All these really cool applications. And so I was you know, sitting there thinking of, okay, what is this postdoc project that I'm going to work on? I said, well, wait a second, there's no reason we can't optimize machine learning pipelines using the same method. You know, I was absolutely certain that this would work, which you should know is generally a terrible idea in academia. You should always expect everything to fail and then be pleasantly surprised when it doesn't. So yeah, so this is a project I decided to work on. All right, and then of course, being an academic, I have to say, yes, of course, other people came up with similar ideas before. There's no such thing as an original idea in academia anymore. But it's mostly been limited to parameter optimization. So if you've taken a machine learning or a data mining course before, you're probably familiar with, you know, the concepts of grid search, where when you're trying to find the best parameters for a model, you specify, okay, explore this parameter range for this parameter and this parameter range for this other parameter, and then you just search through. You try out all possible combinations, right? It's a brute force search. Really dumb, but you know, eventually you'll find a good answer. And that's been the standard for a very long time. And then people found out, oh, actually, if you randomly sample within those combinations, you can typically find the best parameter setting faster by randomly sampling in there. And of course, where there's room for random search to work well in a search problem, you can do, you know, fancier techniques like Bayesian optimization or what I use, evolutionary computation. And so there's a couple methods out there called AutoWeka and AutoSKLearn, also worth checking out. AutoWeka is for, guessed it, Weka. AutoSKLearn is for Python, that use Bayesian optimization to do a very similar thing to what I'm about to talk about. So I decided I wanted to make a tool to solve this problem, and I called it TPOT, which is short for the tree-based pipeline optimization tool. I'll explain where the tree-based part comes from. But basically the idea here is we want to try to automate as much of the machine learning pipeline as we can. So going back to that depiction of a machine learning pipeline before, it's going to try to automate the feature selection, the feature construction, the feature preprocessing, the model selection, and parameter optimization for you. Right, so a pretty big chunk of the machine learning pipeline design. You still have to clean the data yourself, woe is us, but we're slowly expanding TPOT out to cover that area as well, although that's much, much harder. So the basic idea of TPOT is, you know, we have this library, scikit-learn in Python, that has all kinds of machine learning operations. So we have a whole bunch of preprocessors like scalars and PCA, and we can cast features into polynomial features and all that good stuff. We have all these different feature selection methods. We have all these different supervised learning models, like decision trees, random forests, SVM, logistic regression. So we said, okay, let's build a data structure that allows us to make machine learning pipelines of them. Actually, scikit-learn, we already have this pipeline data structure, so we just use that. And then